This is Experimental Psychology, Week 3, going over 3 claims and the 4 validities. So before we talk about the claims and the validities, we just need to briefly cover some more terms. When we talk about variables, we can talk about measured variables. So these are like survey responses. These could be observations that we're taking of people out in the world. These could be physical measurements like the level of cortisol, which is a stress hormone in your blood. And we can contrast this with manipulated variables. So these are variables that are imposed on the participants by the researcher. So you can think about this as sort of your experimental manipulation. Whether or not you get the drug treatment or the placebo would be a manipulated variable. The important thing here is that not all variables can be manipulated, right? So we can't manipulate gender, we can't manipulate socioeconomic status. And then sometimes we both measure and manipulate. So perhaps I'm interested in inducing stress to measure the effects of stress on coping mechanisms or something. And I take one group and I stress them out and the other group I don't. I might measure their stress just to verify that this manipulation worked. So just be aware that these are some of these terms that we use. Now, the 3 claims that we're going to talk about are frequency, association, and causality. When we talk about frequency, these are just descriptive statements. So if you think back to statistics, we're talking about description. There's no manipulation, right? For example, minimum wage workers are mostly teenagers working part-time. This is another instance of that frequency claim from the 2010 annual socioeconomic study. And this data actually shows that that first claim is not true, that minimum wage workers tend to be overwhelmingly over the age of 20. And what I bring up here, the reason why I bring this up here is that oftentimes people make frequency claims that are anecdotal. Everyone that I know who works for minimum wage is a teenager. And that's an anecdote. And generally speaking in science, we prefer facts and data over anecdotes. The next frequency claim, or the next claim, is associative claims. These are claims about relationships between variables, the degree to which 2 variables vary together, or in other words, if I know something about one variable, what does that tell me about another variable? So for example, teenage pregnancy rates have been decreasing over time. And when we look at this, and this is true data, we find a pretty strong negative relationship. As time increases, teenage pregnancy rates are going down. And this would be an associative claim. Now, when we talk about association, we're really talking about correlation. So if you've had statistics yet, then you sort of know what we're talking about here with correlation. Correlation can range from -1 to +1, with +1 being a perfect positive correlation, -1 being a perfect negative relationship. So for example, there's a relationship between class attendance and class performance. In other words, if I know something about your class attendance, I can also know something about your performance. This is a positive relationship, so as attendance goes up, performance also goes up. Now in the middle between -1 and +1 is 0, which is no relationship. So as your correlation, your association gets closer to 0, then there's no relationship, or a weak relationship. So a correlation of 0.14 or 0.20, that would be considered a weak relationship. One thing to be aware of is that correlation does not equal causation. So for example, there is a positive relationship between ice cream sales and drownings. Now obviously ice cream sales don't cause people to drown. I don't imagine people are sort of out in the middle of the ocean trying furiously to hold their ice cream cone up while they're swimming and then end up drowning. And I don't think that, people drown and that causes a spike in ice cream sales because people are sad. There's a third variable here that causes both of these things, or a third variable that affects this relationship. And that variable is temperature. It's summertime. When it's summertime, people go swimming more likely, that increases the likelihood of drowning, and people consume more ice cream. So just be aware, just because 2 things are related doesn't mean that one causes the other, right? It could be that one causes the other or the other way around, or it could just be some third variable causes both of those things. Now, when we talk about causality, we're no longer talking about a relationship. We're not just saying there's a relationship between attendance and performance. Now we're actually saying that attendance causes performance, right? Because it could just be, maybe I'm a terrible teacher, and maybe that attendance has no relationship on performance. And in fact, that it's just the students who would perform better anyways tend to be the same students who come to class. All right, so when we're talking about causal claims, we're talking about making a specific causal prediction. So another example here would be that raising the minimum wage would lead to job cuts. This is an anecdotal causal claim that you often hear from politicians, especially conservative politicians. This is somewhat controversial because when you look at the actual data, this claim is not necessarily supported. Now, in order for a causal claim to be considered valid, we have to meet three criteria. The first criteria is covariance. So the two variables do have to be related. Covariance is just a fancy word for a correlation. The two variables have to be correlated together. Temporal precedence is just the idea that the cause has to come before the effect. In order for a causal claim to be valid, the thing that you say is doing the causing has to come before the thing that is being caused. And then the last one is internal validity, and this is the most difficult of the three criteria for causality. And internal validity says that the causal variable in your study must be the most plausible cause. In other words, you have ruled out or you've controlled for all other possible causes, right? So the idea here is that, when we're studying our dependent variables, which we'll get to in a minute, when we're studying our variables, oftentimes there are many, many things that can cause a particular outcome. You can think of aggression, for example. There are many, many things that cause aggression. So if you want to do a study that shows that video game violence leads to increased aggression or causes increased aggression, then you're going to have to control for all of the other things that could potentially be causing that aggression. And we'll talk about that later on and how we do that. So we'll talk about the 4 validities, but you'll see on here that there are only 3 validities because I'll save external validity for next week. So when we talk about construct validity, the question that we're asking is, does the measures in our research, does our study actually measure the thing that it's designed to measure? So construct validity is really about evaluating the tools that we are using to measure our variables. Does the Beck Depression Inventory truly measure depression and not anxiety or a bad mood or something else like that? So face validity is just, does it look like it does? Like if you read through it and it asks, are you depressed? You'd be like, yeah, sure, I'm depressed. That would be face validity. Criterion validity is about how well the measure predicts performance. So for example, if the SAT and the ACT do a good job measuring academic ability, then it should predict how well one does in college. Turns out that it does, but only for the first semester freshman year. Every semester after that, the criterion validity of the SAT and the ACT gets weaker and weaker and weaker. Another way that we can sort of demonstrate that our measure, that the tool that we're using to assess a construct is valid, is through convergent and divergent validity. This is essentially showing that our tool functions in a similar fashion to other similar measures and does not function similarly to different measures, right? So for example, if I give someone, if I create my own measure of intelligence and I give someone a big battery of tests, my measure of intelligence should be related to GPA. It should be related to the SAT and the ACT. It should be related to another intelligence test. If I have data that shows that, then I can say that my measure has convergent validity with these other measures. On the opposite of this, if I have some measures of depression and anxiety or memory, for example, I would show that my measure of intelligence is not related to depression and anxiety, and it's not related to memory. And that would be divergent validity from those measures. Now, we talked about this idea in early on in the class, that in psychology, oftentimes we are dealing with abstract concepts, and so we have to develop measures to assess these constructs. And one thing that's important to be aware of when you are doing research is that when you're measuring these constructs, let's say for your project you're measuring depression, and you go out and you get a bunch of people's ratings on depression and you get a depression score for them. That score that you get is going to contain some of their depression, right? It's going to capture some of that depression, but it's not going to capture all the depression. That score is also going to have some error built into it. And so we're going to talk about true scores versus error. So the actual score that you get from the participant, that's the raw score, that's an observed score, right? Survey, anything like that. Now, or for example, a person's weight. So if I'm doing a study on weight and I have people come into my lab and get on a scale, that weight that I get for each participant would be the observed score. But within that observed score, there are two components to that observation. There's the true score, and then there's error, right? The true score you can think of being like the actual person's depression or their actual weight. Variability in that score that's related directly to the construct we're trying to measure. Error, on the other hand, is variability that comes from sources other than what we're interested in, right? And there are two types of error that we talk about, random error and systematic error. So for example, if I asked a class, what would affect people's weight, oftentimes people will say things like, well, when you last ate, right? So if I bring someone into my lab and I'm trying to measure their true weight at this time, and I get an observation of their weight of 200 pounds, well, some of that weight's going to be their true weight, but some of it might be when they last ate. Maybe they went to Grand Lux Cafe downtown and had a giant pile of food before they came into my lab. Or maybe they've been drinking a lot of water, so they're retaining a lot of water, right? That is variability in the score that I'm observing that's unrelated to their actual weight, right? If I measured them again, that would be different. And that would be random error. Systematic error is error that occurs consistently for all people in the sample, or consistently for all people in one condition of the experiment, which we'll talk about. So you can think of this as sort of scale calibration. If my researcher who in my weight study was supposed to be calibrating the scale and calibrated it 2 pounds under, so that every participant who came in, we measured them 2 pounds below what their actual observed weight was, right? That would be a systematic error that's affecting everyone. Now, so what this means is anytime we have an observed score, anytime we measure anything, we're going to have true score, systematic error, and random error. Ideally, what we want to do in our studies is reduce the amount of systematic error. Because when we reduce the systematic error, what this means is that the observation that we're getting contains more of that true score construct we're looking for. When we increase systematic error, then what we're doing is we're pushing out the true score, and we just have more variability in there that's related to something about the study, something that we did wrong, or we introduced error into our measurement. Now again, this is all abstract. We'll talk later on about specific ways that we do this. Another thing to notice here is that we can't really have an effect on random error, right? Random error just happens when we're doing our studies, right? It's just noise in the data. It's that person's particular mood that day when they came into your study. And there's not much that we can do about that. Although we'll see at the end of this lecture, there is a way that we can sort of distribute that random error equally among our experimental and control conditions. So next we'll talk briefly about statistical validity. So the thing about statistical validity is that anytime we're making claims, we're making probabilistic claims, right? We're saying that our statistics tell us that the probability that we are wrong is less than 5%. If you recall, p is less than 0.05, right? This is less than 5%. We're making a claim, there's a probability that there's no relationship or that there's no causal effect, right? P is less than 0.05 is 5% chance that you are wrong. Let's say you do a study and it turns out that God opens up the heavens and tells you that you are wrong, right? There is a 5% chance of that happening. Well, maybe not God opening up the heavens, but there's a 5% chance you'll do a study and get a significant relationship even though it's not true. And we call this a type 1 error. The way to think about this, I like to use a pregnancy test analogy, right? Imagine that you think you might be pregnant, so you go and you take a pregnancy test. And when you get the results of the pregnancy test, it says you are pregnant. So you go to the doctor, and the doctor uses a much more sophisticated test, a much more precise test, and finds out that actually, no, you're not pregnant, right? This would be a type 1 error, right? The study tells you you have a significant result, but it turns out that that's not actually true. It's like a false positive. The other side of this is a type 2 error, right? And this is a false negative. So again, using the pregnancy test analogy, you go and you take the home pregnancy test, and it says you're not pregnant, but then you go to the doctor, and the doctor says, nope, that test was wrong. You actually are pregnant. That's a false negative, right? The test said it wasn't a significant result, but turns out that it was. Now, statistical validity depends on these two really sort of big ideas in statistics, and these are power and effect size, right? So power is your ability to get a significant result. Like if there was a significant result out there to get, power is your ability to find it. The analogy to sort of think about is imagine that you are looking for something in a dark room. Power is your flashlight. The brighter the flashlight, the easier it is going to be to find the thing you're looking for in the pitch black room. Effect size, on the other hand, is the thing that you are actually looking for, right? It is the effect that you're looking for out there in the world. And the size of the effect is essentially related to the strength of the phenomenon. If it's a weak effect, it's going to be small. If it's a huge effect that happens, all the time, then that's going to be a big effect. So, for example, later on in the semester, we're going to do a parking lot study where we're going to go out into the world and we're going to ask the question, do people take longer to pull out of a parking spot when someone is waiting versus not waiting? And what we're going to find when we do that is that indeed people do take longer. That's a huge effect. We find it every semester. There are other effects that might be more subtle, more small. And for those small effects, you're going to need more power to find them. Right? Bigger effects are easier to find, right? So for example, if you've got a tiny little 1990s flip phone screen that you're using for a light in that pitch black room, and you're trying to find an elephant, a giant effect, you'll probably find it, right? You have low power, but the effect is so big, you'll find it. But if you're looking for an earring, you're probably not going to find that earring with that low power flashlight or study. On the other hand, if we're looking for that earring, but we have a giant, bright 10,000 candle power flashlight, then we're going to be likely to find that effect. And so our statistical validity depends on this power and effect size. Power is effectively your sample size. The larger the sample, the easier it is to find smaller effects. So the last one we'll talk about is internal validity, and I'm just going to walk through an example of an experiment. So when we're talking about internal validity, we're talking about the degree to which we can say our independent variable is causing our dependent variable and not some other variable. So the degree to which x causes y. So for example, what we want to be able to do is rule out third variables. So the number of churches is directly related to increased crime rates, and this is true. And the reason for this is population. As populations go up, both crime rates and the number of churches in the community also go up, right? And so what we want to do in our experiments is control for as many of these variables as we can so that we can say our independent variable is the thing that is doing the causing. So the basic logic of an experiment is we take two identical groups, we give one of the groups a treatment, we do something to the one group, they're identical at the beginning, and then we measure them at the end. And if there's a difference between the two groups, then what we can say is that whatever we did to group one is what caused the differences in measurement after the experiment. We call this the experimental group. We call this the control group. Okay. Now we're going to go through an example real quick of how this logic works out. So let's say I have this idea that caffeine improves mental functioning. I'm making a prediction that caffeine consumption is going to affect mental functioning. Now, if I were doing this study for my project, right, I'd want to talk about operational definitions, right? Caffeine consumption is kind of arbitrary. Mental functioning, it's kind of abstract. So we'll say that drinking 2 cups of coffee might be our definition for caffeine consumption. And we'll use an intelligence test as mental functioning. Now, I'm making a prediction that caffeine is going to cause increased mental functioning, right? But it could, of course, always be the other way around, right? Just because we find a relationship, let's say, between increased mental functioning and caffeine, doesn't necessarily mean that caffeine causes increased mental functioning. In order to determine this, right, we have to manipulate that caffeine consumption. We have to manipulate the variable that we think is having an effect on the other variable, right? Typically, when we're doing an experiment, the thing that we manipulate is going to be what we call the independent variable, right? So in this example, what we'll do is we'll break the people up into 2 groups. One group is going to get 2 cups of coffee, the other is going to get nothing. Okay. The variable we think is doing the causing, we call that the independent variable. And the thing that we think is being caused, that's the outcome, that's the dependent variable. The dependent variable depends on the independent variable. Now here's the thing though, right? We talked about this idea of internal validity. We want to be able to say that our independent variable, caffeine consumption, is the thing that is causing increased mental functioning. But there are other variables in our study that could affect increased mental functioning. So often when I do this in face-to-face classes, I'll say, what other variables do you think could influence increased mental functioning? And students will often say things like caffeine sensitivity or the amount of sleep that you got the night before. And those are things that we would talk about as being random error. Those are things that do affect increased mental functioning, but not systematically in our study, right? They affect mental functioning. Those are what participants bring to the research scenario. But if you think about our setup that we have here, so half of the group is getting 2 cups of coffee, the other half is getting nothing, and then we're measuring their intelligence scores using our intelligence test. Our groups are different on more than one variable. They're not just, the group that gets the coffee is not just getting caffeine, they're also getting hot water, right? And the other group isn't getting hot water. They're also getting all the non-caffeine components of coffee, and the control group is not getting any of that. And so this is a problem for us because what this is this is a systematic difference between our experimental group and control group, right? If we find, let's say, that the experimental group did have increased mental functioning, we would not be able to conclude that it was caffeine. It might be caffeine, but it might also be hot water because the experimental group got hot water and the control group did not get hot water. And what we call these confounds, right? These are confounding variables. They're an alternative explanation for an effect, right? I say it's caffeine, but a reviewer might come around and say, no, it's probably just hot water. And you can't rule that out. And this confound is a threat to internal validity. It threatens our ability to say, no, it is our independent variable that is doing the causing. So the way that we control for these confounds is we want to make our groups as identical as possible. Now, we'll talk about these other individual characteristics, these extraneous variables. These things could influence the dependent variable, but we have a way of controlling for those. All right, so what we want to do to control for these confounding variables is we want to make the groups as equal as possible. The idea behind the experiment is that if the 2 groups are completely equal at time 1, and then we see some effect at time 2, then the only possible reason we can expect that is because of the manipulation, because of the independent variable. So what we could do is make 2 pots of decaf coffee using the same exact methods, using the same exact beans, the amount of hot water, and then we could add caffeine to one of those. And then that way the experimental group gets decaf coffee with caffeine, and the control group gets decaf coffee. So they get all the same stuff, the hot water, the non-caffeine components. It's all exactly the same, except the only difference is the presence or absence of caffeine. And this eliminates confounds because the groups are identical except for the independent variable. Another way that we can make the groups identical is through random assignment. Random assignment to conditions actually helps control for all of those extraneous variables, right? The amount of sleep that a person got the night before, the sensitivity to caffeine and the like. So for example, if we randomly assign people to groups like this, and they go in there, and if we gave them an intelligence test now, what would happen is they would score equally on the intelligence test at this point if we just randomly assign them. If we asked them how much sleep did they get the night before, they would score equally on that. Because what random assignment does is it takes and it distributes these characteristics equally across the groups. So one person in group A might not have slept very well, but there'd probably be the same person in group B who didn't sleep very well. And on all of these characteristics get equalized over these groups. And this effect gets stronger as the sample size gets larger. Right? Random assignment is a really powerful way of controlling for all of these individual different characteristics. So if we randomly assign people these 2 groups, and the experimental group gets caffeine, and the control group gets nothing, and they're identical before, then what that means is if we see a difference between the intelligence tests for the 2 groups, then we can conclude that it's actually the caffeine that is doing the causing, because nothing else is different between the 2 groups. Now, one thing to be aware of when I talk about the dependent measure, I'm talking about the average score of the intelligence test for Group A compared to the average score of the intelligence test for Group B. I'm not really interested in individuals' scores, whether your particular score changed from time 1 to time 2, right? So what's cool about this is with random assignment, we know that groups are equal on the dependent variable before the manipulation, and so we don't actually even need to measure it beforehand. Right? We don't need to know if their score changed. That is a research design we could do, but it's not something we have to do. As long as all the groups are equal beforehand, then any differences after the manipulation are due to the manipulation, and we can make these causal claims. So that is it for this week's lecture. We will meet next week, and we will go over what we need to work on for the final project. As always, make sure you're reading the chapters and taking this week's quiz as many times as possible.